welcome back. This is lesson 7.7, transforming exponential and logarithmic functions. Back to our favorite thing again. The objectives for this lesson: by the end of this lesson, you'll be able to transform exponential and logarithmic functions by changing the parameters. You'll also be able to describe the effects of changes in the coefficients of exponents and logarithmic functions. You can perform the same transformations on exponential functions that you performed on polynomials, quadratics, and linear functions. All right, let's just do a quick warm-up to kind of review what we already know. So the question says, how does each function compare to its parent function? So first of all, we have to decide what the parent function is going to look like. And in the first problem, we see that there's an exponent of 2. So that tells me that it's going to be a parabola, because the highest exponent on a parabola is 2. All right, so now that I see that, let's look and see what else has happened to this parabola. Well, first of all, I can see that it's vertically stretched by a factor of 2. How do I know that? Well, I see this number is multiplied by everything. And when something is multiplied, that means it's either going to be a stretch or a compression. Since this 2 is bigger than 1, that tells me that it's a stretch. If it had been like a half or 2/3, that would be less than 1, so it would be a compression. But it's not. It's more than 1, and so it's a stretch by a factor of 2. All right, the next thing I see is this 3 snuggled up in parentheses with my x. So that tells me this is going to be a horizontal, and it's going to be translated 3 units to the right. Remember, horizontal is horrible, so even though it says -3, that means we're actually going to move to the right. And then finally, after all of that, we have a -4 at the end, so it's going to be translated 4 units down. The whole thing is going to go 4 units down. So there we have our translation there. All right, for the next problem, we can see that this highest exponent is a 3. So that tells me my parent function is going to look like this. For a cube, this is what the parent function looks like. All right, and the first thing that we see is this minus snuggled up here with my x. Okay, so that means the x's are going to be opposite. So if I have an x on this side, I'm going to have the opposite on the other side. So notice my points are going to move. Everything's going to move across the y-axis. All right, so I have a reflection across the y-axis. And then at the very end, I have a +1. So that tells me it's going to be translated 1 unit up. All right, so it would move up. It would actually move across this way. And then the new one would be moved up 1. That's terrible drawing, but you get the main idea. Okay, let's keep moving. Okay, here's our chart. We've seen this chart before, and it hasn't really changed that much. The only difference is today we're going to be doing exponential functions. Okay, so let's look at the vertical things first, because vertical is good. We're going to look at vertical translations and the vertical stretch or compression first. All right, remember, vertical deals with our y. Okay, so you're going to take your y, which is, we call it f of x, and just add to it. And that will move our entire function either up or down, depending on what we have. If we have +3, it goes 3 units up. -6, 6 units down. Really simple. Same way, if we have our y and we multiply something to it, that's going to tell us a vertical stretch or a vertical compression. Remember, a stretch if it's greater than 1, and a compression if it's less than 1. So in our examples here, you can see y equals 6 times 2 to the x power. So it's just going to be a stretch by 6. All right, so when you multiply, you're getting a stretch or a compression. Okay, let's look at our horizontal translation and our horizontal stretch and compression. Now remember, horizontal is horrible, so everything's going to be a little bit different. Okay, so what we're going to do, if we're doing with horizontal, we're dealing with our x. And our x, remember, is the exponent, actually, in this case. Okay, because it's an exponential function. So what we're going to do, if we're doing a horizontal translation, we're going to see the h snuggled up in here with our x. So in this example, we see 2 to the x minus 2, and that tells us it's 2 units right. Even though it says minus and we think it's left, it's going to go 2 units right. And again, if we have x plus 1, we're going 1 unit left. But the main thing is, it's actually, even though we don't put the parentheses up here necessarily, it's actually tied in with our x's, so it has to do with the horizontal translation. Okay, again, if it's multiplied, if there's something multiplied by our x, then it's going to be a stretch or a compression. And since it's multiplying by the x, which deals with the horizontal, it's going to be horizontal. So look over here at our example. We see 1/5 is multiplied by the x. So the x is horizontal, and when you multiply, that tells us it's going to be a stretch or compression. Now the question is 1/5 a stretch or compression? Well, your immediate thought might be it's a compression because 1/5. But remember, horizontal is horrible, so we have to actually take the reciprocal before we can decide whether it's a stretch or compression. And in this case, when we take the reciprocal, we actually have the number 5, which is greater than 1, so it's a stretch by 5. In this example, we have 3 times x. The 3 is multiplied by the x, which tells us it's horizontal. And before we can decide whether it's a stretch or compression, first we have to take the reciprocal. So actually, it would be 1/3. 1/3 is less than, so it's a compression. Remember, less, compress. Okay? All right, so finally we have our reflections, and just like before, notice if it's across the x-axis, let's just draw a picture of this real quick. We have x and y. Okay, if it's going across the x-axis, that means our x is staying the same and the y is going to be opposite. Y would be up here and y would be down here. So in our problem, we're going to take our y and just take the opposite, or minus, okay? So we can look at the example here. Y equals -2 to the x power. Now, for the reflection of across the y-axis, when we go across the y-axis, I'm going to just erase this. When we go across the y-axis now, we see that we're going across this way. This is our y, this is our x. All right, and now my x's are going positive to negative. So here we have to put that negative snuggled up with our x in there. Okay, and notice our x is up here in our exponent, so we put it in front of our x here. So this table should be pretty familiar to you, and all those things should be pretty familiar. The only thing that's different is where those translations that the x is acting as the exponent now. Our variable is the exponent. All right, let's go. Let's try an example. It says, make a table of values and graph g of x equals 2 to the -x plus 1. Describe the asymptote and tell how the graph is transformed from the graph of the function f of x equals 2x, which is, by the way, the parent function for an exponential. 3 of x could also be used as the parent function too, just for your information. Okay, so let's talk about what we need to do. Now, I'm not going to have you actually make a table of values because I know you can just put that in your calculator and click second table and you can see what the table looks like. So I'm not going to have you do that, but let's go ahead and talk about here is what the table should look like, and you can actually put that in your calculator and see that. And so let's take a look at the picture of the graph. All right, so here's our graph. The parent function is the one in blue, okay? This is f of x equals 2 to the x power, and that's this one in blue, okay? And notice that the asymptote, that's the line that our function never actually will touch. It'll get infinitely close to it, but will never actually touch. And so here our asymptote is y equals 0 for the parent function. But look what happens. We took our parent function and we went up 1. So our new asymptote is going to be y equals 1. It's going to be the vertical change. All right, and here the vertical change is plus 1. So our asymptote is going to be y equals 1. And the graph approaches this line as the value of x increases. The transformation, okay, so we also have Notice this is going to be a reflection, and it's going to reflect the graph across the y-axis and moves the graph 1 unit up. Okay, let's take a look at another example. All right, try this one on your own. Make a table of graphs, a table of values, and I'm not going to require you to do that, but I do want you to see the graph, and I want it to be pretty neat so you can see what's happening. Okay, so you're going to take the parent function and graph that one first, and then you're going to have to graph this one, and then I want you to tell me how the graph is transformed. I want you to be able to tell me in words how the graph was transformed, and tell me where the asymptote is. So take a look at that. All right, so I went ahead and here's your table of values, and you should have seen that in your calculator pretty easily. So let's take a look at what you should have come up with. I hope that you found this pretty easily. All right, so we see that the asymptote is y equals 0. Notice I didn't have anything added on vertically here, so I didn't change my asymptote, all right? So the parent function, which is here in blue, and our new function, which is the red one, is going to be, they still have the same asymptote, and that's this line in green. So the asymptote is y equals 0, and the graph approaches this line as the value of x decreases. The transformation moves the graph 2 units to the right, okay? So it's a horizontal movement, 2 units to the right, okay? It's minus, so it tells us we're actually going this direction. All right. All right, let's try this example. We're going to graph the function, then find the y-intercept and the asymptote. We're going to describe how the graph is transformed from the graph of its parent function. So here is the new function. So what is the parent function going to be? Well, let's just let our parent function be f of x equals 1.5 to the x power. All right, so now let's see if we can figure out what's going to happen to it. I see some things that are multiplied by the whole parent function. So I know that I'm multiplying, and so that tells me that it's going to be a stretch or compression, and I'm not multiplying my x, I'm just multiplying the whole thing. So that's telling me that it's going to be vertical. So we're going to have a vertical. Now, is it going to be a stretch or compression? Well, 2/3 is less than 1, so it's going to be a compression, a vertical compression. Now, have we done anything horizontally? No, we have not. So let's take a look at what's happened. All right. Let's take a look at it. So first of all, we see that the graph of g of x is the vertical compression, which was what we just said, of the parent function by a factor of 2/3. All right. Now, when we look at the graph, we can see that the asymptote is 0 because notice there was nothing vertically changed here, so the asymptote stays the same. All right. So how do we find the y-intercept? Well, remember, to find the y-intercept, you ask the question, what is y when x is 0? Okay, so 1.5 to the 0 power is 1, and 1 times 2/3 is 2/3. So we can see that our y-intercept is 2/3. So when x is 0, y is 2/3. So our new graph is going to have the y-intercept right there. Okay, so take a look at this example. Don't be freaked out by the e, because remember, e is just the same as 2.718. And so let's just start thinking about this problem. First of all, let's think about what our parent function is going to be. Let's let our parent function just equal e to the x. So you could go ahead and plot that in your computer, in your calculator, y equals e to the x, and graph that. All right, and then let's look at the rest of this, the information on what we can find out about this. So our new graph is going to have a y-intercept of e. Now, how would that be? Well, remember, to find the y-intercept, you say, what is y when x is 0? So if x is 0, y is going to be e to the first power. And so that's going to be 2.718 to the first power, which is 2.718. So when x is 0, y is 2.718, right about there. Okay, now this is a little bit crazy because we got a couple of things going on here. So notice that I have this x is got the negative sign in front of it. That means that my x is reflecting across the y. All right, so this is going to reflect across. So here I have 1, 2, so I'm going to reflect it over 1, 2, okay? Now, let's notice this. This says plus 1, and we usually say, well, that's a plus 1 because it's horizontal. But in this case, since we've reflected, and so now we're actually doing the opposite. So in this case, we actually are moving one place back over to the right. And I know that's kind of odd, but this negative sign, because it's reflected, makes this one actually move over. And I'm not going to give you a really complicated one like that one on your test, but it is one just kind of interesting one for you to do. So, and notice that the range stays is y has to be greater than 0, and our asymptote is y is 0 on both of them because there's nothing else added vertically at the very end of this function. All right, here's one for you to try on your own. Turn your video off and give it a try. Okay, so the first thing we want to do is you could go ahead and graph your parent function. So what do you want to do for your parent function on this one? Well, let's say that our parent function is y, or f of x, equals 5 to the x power. So I hope you were able to get that in your calculator. So that's our parent function. Now we're going to need to find the y-intercept of this new function that we need to find. So in order to find the y-intercept, we always ask, what is y when x is 0? Well, if x is 0, that would be 5 to the 0 power, and 5 to the 0 power is 1. So 1 times 1/3 is 1/3. So our y-intercept is going to be 1/3. All right, next it says to find the asymptote. Well, notice that there's nothing added on here, nothing vertically added on to our asymptote. So our asymptote is going to remain y equals 0. All right, next we have to describe how it's transformed. So we can see that something is multiplied here. And so this is multiplied by our whole y. And so that tells us it's vertical and it's less than 1, so it's a vertical compression. Notice there's nothing else that has happened to my x, so that's all we're going to have on this one is a vertical compression by a factor of 1/3. So let's take a look at the graph of this. And notice the asymptote stays at y equals 0. Nothing really tough on this one. It says it's a vertical compression of the parent function by a factor of 1/3, just like what we said. All right, next. Okay, here's another example. Turn off your video and give it a try. Okay, on this one, first of all, we want to figure out what our parent function is. So let's let our parent function be 2 to the x power. All right, so first of all, we want to find out what our y-intercept would be. So our y-intercept is going to be what is y when x is 0. So if x is 0, 2 to the 0 power is 1. 1 times 2 is 2. So our y-intercept is equal to 2. Next, we need to decide what our asymptote is going to be. And notice there's nothing vertically added on here. And so our y-intercept, or our asymptote is going to be the exact same as our original function, which is going to be y equals 0. All right, now we need to talk about what happens here. Notice I have a 2 multiplied by this y, my parent function, and so that tells me it's a vertical. Now 2 is greater than 1, so it's a vertical stretch. Okay, also my x has got the negative on it, so that tells me that my x is going to go from positive to negative or negative to positive, so that's a reflection across the y-axis. All right, so here's what the graph, your graph should have looked like. And the graph is a reflection of the parent function, f of x equals 2 to the x power across the y-axis and a vertical stretch by a factor of 2. All right, so because a log is an exponent, transformations of logarithms are similar to transformations of exponential functions. You can stretch, reflect, and translate the graph of the parent logarithmic function, f of x equals log x base b. All right, so here's our table again. Again, same kind of thing. If we add to the end, it's going to be go either up or down, and in this case it would be 3 units up or 4 units down. So that's your vertical translation. Vertical stretch, same thing. You multiply it by the outside. If it's greater than 1, it's a stretch. If it's less than 1, it's a compression. Same exact thing. Okay, the only thing different again is our horizontal. Notice I have my horizontal snuggled up inside my parentheses with my x. Same thing. If it says minus, we're going 2 units to the right. If it says plus, 1 unit to the left here. Okay? And now again, the horizontal stretch, so it's multiplied. Remember, the multiplication on a horizontal we have to do the reciprocal of it. So in this case, notice it's multiplied by our x, so that tells us it's going to be a stretch or compression. We can't just look at the 1/5, we have to do the reciprocal first. So that would actually be 5 in the end. So this is a horizontal stretch by a factor of 5. Here we have 3 multiplied by our x, so again it's multiplied, so that tells us it's a stretch or a compression. We can't tell until we do the reciprocal. The reciprocal is 1/3, that's less than, so it's going to be a compression. Again, the reflection, if it's going across the x-axis, that's a change in our y, so we just do the negative of the whole thing. And if it's across the y-axis, the x is going to be the opposite, so we have to snuggle that minus sign up with our x in the parentheses. All right, same kind of stuff. Remember, the transformations of ln x work the same way because ln x means log e, or log x base e, okay? All right, this time we're going to do an example transforming logarithmic functions. All right, so we're going to graph each logarithmic function. So the first thing you probably should do before you can graph each of these, you need to figure out what the parent function is. So if our new function is here, our parent function, let's let our parent function say f of x equal log x. All right, so that's your parent function. So you can just put in your calculator y equals log x. All right, and when you type that in and then put your other one in for your second y equals 5 log x minus 2, when you graph that, you're going to see something that looks like this. So your first one, log x, is going to look like this. Now let's talk about our asymptote. Before, when we were doing exponentials, our asymptote was actually a y. All right, but now that we're doing the inverse, our asymptote is going to, y equals. So now that we are doing the inverse of our exponent, the log functions, our asymptote is now on the x, it's going to be on the x. Okay, so in this case, it's x equals 0. All right, now let's talk about what has happened to our new function. Notice that we've multiplied it by 5. So we're going to have a vertical stretch because it's greater than 1 by a factor of 5. And then notice over here it says minus 2. Okay, so that means we're going to just move our graph down 2. But we didn't shift it left or right. So when you're doing log and you're not shifting left or right, that's why our asymptote stays at x equals 0. Okay, we just moved it down a little bit. So let's take a look at what this says. The graph of g of x is a vertical stretch of the parent function by a factor of 5 and a translation 2 units down. All right, let's take a look at this example. Notice that this time it says ln. Now remember, ln is equal to log e. So those mean the same thing. Okay, so our parent function is going to be f of x equals ln x. All right, so that's your parent function. So in your calculator, you could type in y equals ln x. All right, so let's see what else we can find out about this. Let's take a look at the graph. All right, so in this particular graph, when we graph both of them, we see here's our parent function. This is y equals ln x, okay? This is ln x. And notice that my asymptote, it's the inverse of an exponential function. So now my asymptote is equal to x equals 0. All right, it's right here. All right, so that's our parent function here in blue. Now our new function, notice that it's going to be the opposite. It's going to move across the y-axis. All right, because we have a minus there, so my x is going to be minus. It's snuggled up, so it's a horizontal reflection across the y. All right, and notice that this 2 is snuggled up inside my parentheses with my x, so it's a horizontal. All right, and again, because of this negative, that makes my horizontal shift, even though we normally would say that was going to the left, because I've reflected, now it ends up being 2 units to the right. All right, and I know that's kind of tricky to remember, so you just kind of have to think about that a little bit. Okay, next. Try one on your own. Turn your video off and give it a try. Okay, so first of all, what is the parent function going to be? Well, the parent function, f of x, is going to be ln x. All right, so you can put that in your calculator first. Now, what all has happened? Well, I see this negative outside of my whole thing, so that tells me I'm going to do a reflection on my across the x-axis because my y's are going to be changed. Okay, so we're going to have a reflection across the x-axis. All right, notice that snuggled up in with my x is a 1. Okay, so we're going to look at the graph and see what happened to that 1. And then in the end, it's going to be a vertical shift down 2. Okay, so let's take a look at what all we see. Okay, so in this case now, before when we were doing the exponents and things went backwards, whenever we saw, when we had a reflection across the y with our x in here, then we had to be really careful about this 1 being plus or minus. Now this time my y is with the x, so we're going to go back to horizontal being horrible, and this says x plus 1, so it actually means the whole function moves over to the left 1 unit. Okay, and so now my new asymptote, now when I'm doing the logs, my x is what's going to determine where my asymptote is instead of the y. So now my new asymptote is going to be x equals -1. Okay, let's see a little bit more about this. The graph is a reflection of the parent function in x across the x-axis, 1 unit left and shifts 2 units down. All right, let's try an example. A new one. It says write each transform function, and let's see what to do. Okay, so it says take f of x equals x to the 4th. All right, f of x equals x to the 4th. It's going to be reflected across both axes, and it's going to move 2 units down. Okay, so in order to do that, we're going to begin with the parent function, f of x equals 4 to the x power. Okay, we're going to reflect it across the y-axis and replace x with, okay, to reflect the y-axis, we're going to place x with -x, okay? And to reflect across the x-axis, we're going to take the whole thing and multiply that by a -1, by a negative. And finally, we're going to translate 2 units down, so we're just going to subtract 2 from the whole thing. All right, here's another example. This one we're going to, again, figure out how to, it says to take f of x equals ln x. It's compressed horizontally by a factor of 1/2 and moved 3 units left. Okay, so what we're going to have to look at is we're going to say, all right, ln x is compressed by horizontally, so that's going to be our x, by a factor of 1/2. Now remember, that's 1/2, so we have to do the inverse of it, so that's how we get ln 2, and it's moved 3 units to the left. That's a horizontal movement, so we're going to snuggle it up with my x, and it goes 3 units left, so we actually put the plus sign in. All right, when you write a transform function, you may want to graph it as a check. Okay, so this is your last example for you to try on your own. So turn your video off and give it a try. Okay, so this one says to write the transform function when f of x equals log x. All right, so we want to translate it 3 units to the left and stretch vertically by a factor of 2. So 3 units to the left means we're going to snuggle up x plus 3. So we're going to snuggle up that into a parentheses like that. And then it's going to be stretched vertically by a factor of 2. So we just have to multiply the whole thing by 2. And there it is. And again, you might want to graph it to see, make sure that it looks kind of similar to what you would think it would look like. Okay, so that is the end of this lesson. I know it's kind of hard, but I think that it's the same thing we've been doing, so hopefully you're starting to catch on how to do these stretches and compressions and translations and reflections and whatnot. So hope you have a great day, and I'll see you soon. Bye.